Welcome to the Cosmic Pie Podcast, Season 4, Episode 20. I'm your host, Wayne Barkhouse. We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota, where summer has arrived. Nice, beautiful temperatures, around high 80s, low 90s for the next 10 days at least. Rather enjoy it while it lasts, especially when you live in North Dakota. Well, today we have a special guest, but before we introduce our guest, just to remind people that we do have a live chat feature that's running. If you have any comments or questions that you'd like to ask us during the podcast, please feel free to send them to us. Robert, explain your time, buddy.
Testing.
Yeah, that's all we're ready to use.
Now we're fun.
And how's that doing?
I can hear you fine.
And I'm talking to one of our guests, the one who's talking, telling us about it. It looks like it's fine. Still nothing but static.
So is your mic? What about the wire on the top?
How about now?
You sound the same to me, but I don't think you're asking me.
No, it's you and I are communicating on different mics. How about now?
You sound the same to me, but I don't think you're asking me.
Okay.
You're echoing.
I'm echoing. Okay.
You're in a time warp.
Well, welcome to the world of doing a live broadcast.
Okay, so do you want to introduce our guest, Robert?
Yeah, I guess I'll start out with that. With us today is, I honestly, I can't remember. It's Dr. Trina Ray, right?
No, just Trina. Yeah, no, only a master's degree. Yeah.
Oh, okay. We've known each other for a long time. We've been a guest at Dragon Con with Space Track and Science Track for a very long time now. We were just
No, just Trina.
19 years?
Yeah, 19, 20 years. Yeah.
And the reason I know she's been with us that long has to do with she has worked on such great projects as Voyager, as Cassini, and we're supposed to be working on Europa Clipper, but stuff happens.
Yeah.
So, yeah, we're apparently still echoing.
Yeah, I can. It's the time delay.
Okay, so the only ones that are not echoing is Trina. So maybe Trina, you can take it over and kind of describe how you got involved in space exploration,
Absolutely.
and then of course work your way up to some of those fantastic projects that you were associated with, like Voyager and so on.
Absolutely. Yeah, no, my very first job at so I worked at NASA's Jet Propulsion Laboratory, which is in Pasadena, California. Probably most famous to folks because it is where we control the robots that we send out into the solar system. So the rovers that are on Mars or things like Cassini or Voyager, a lot of them are run out of JPL. And my background is that I was a local student at the university in physics with an astronomy minor, and I went to apply for a job at JPL, and I was lucky enough to land one on the Voyager Neptune encounter. Which, by the way, that is a crazy, crazy place to start your career. Kind of like the best mission of all time on the last of its great encounters. That was truly what a privilege to have had that as part of my career. Then I went on to work on Galileo for a short period of time. I was on Cassini for decades. I started as a low-level sort of, instrument operations person, and then worked my way onto the science planning team, and then up to the science planning team chief by the end of the mission. And especially was interested in the moon Titan, and I got assigned to work on Titan early on, and I worked all 127 Titan flybys, either as a science planner or as the chair of the Titan orbiter science team. And then as Cassini's rolling towards its end of mission, I had a role in the grand finale. That was that extraordinary mission where we plunged the spacecraft between the planet and the rings. I was one of the key strategic architects of that. And then as the mission came to an end, I started on Clipper and worked on Clipper as an investigation scientist, and also worked as the deputy science manager, and got Clipper through launch. And that's how I wrapped my career at JPL about a year after the Clipper launch. So that's my short history of all the amazing missions that I've worked on. But as you can see, it's all been outer planets and flagships. So it's all been big missions out of JPL.
Cool. And I will now ask, how are we sounding to everybody out there now? Because I've played as much as I can with these freaking mics. Short of shutting us down and coming back up.
You sound fine to me, but I think you always did.
Do you want to, Trina, while we're waiting to make sure the audio is working, you want to say a little bit more about Voyager's encounter with Neptune in 1989?
Oh my gosh. Oh, Wayne, what a gift that was. So Voyager launched in 1977, right? So like 50 years ago. And it does the two Voyager spacecraft, both of them do great flybys of Jupiter, both of them do great flybys of Saturn, and then one of them goes on to Uranus and Neptune. So so basically the team had been together for 30 years, or, including building the spacecraft and operating the spacecraft. This is the sixth encounter that they've done together. Everybody knew everybody. Everybody knew how to do their jobs. The spacecraft was fantastic. And, there were surprises. I mean, it's sort of Neptune being so blue and yet still having one of these storms on it that was orbiting faster than the planet is orbiting, right? It's tied to the inside of it. And then also knowing that you're going to send the spacecraft off over Triton, and then you're headed out into the outer solar system, that this is the last big thing that you'll do. And then Triton had geysers, nitrogen geysers on it. Oh my gosh, crazy stuff. And then also Voyager is just one of those missions that speaks to, I don't know, I guess the way that I usually put it is it speaks to the humanity in us because of the golden record and the fact that Voyager is going to exit the solar system. And at some point, our star, right, is going to evolve into a red giant. It's going to swallow the Earth. And if humans aren't off the Earth by then, we will have a very bad couple of years. But Voyager is that's not going to affect Voyager at all. It's still going to be out there. Very hard, of course, for somebody to find it. It's still sending signals back to us every day. Still working every day. We're slowly but surely shutting off various instruments to keep the power on for the transmitter and the computers. And both Voyagers have exited the solar system, so sort of a milestone for mankind, right? Like, if you think about it, in the history of the species, there's only One time. That is the first time that the species steps on another world. And that happened in our lifetimes. Well, I don't know for you young gentlemen, maybe not for you young gentlemen, maybe not in your lifetime. And I was very young. I was just a baby, so I don't remember it. But when they went to the moon, right? That was the first. I mean, that will be taught in the history books for the rest of our species. I mean, that's an amazing thing to think about. And then Voyager exiting the solar system. The first time. There's only one time in the history of the species that you send an avatar outside of the solar system. That happened in our lifetimes. So
Yeah, so
Voyager is incredible.
right. So now we have Voyager 1 and 2. Of course, we also have Pioneer 10 and 11, and also the New Horizons spacecraft.
Right.
So we have 5 and counting vehicles that have reached escape velocity and will never return to the inner solar system.
But have they all exited the solar system though?
No,
Wayne?
but they
I'm not
will
sure.
eventually.
I know the
They will
Horizons
eventually, right?
are,
Because the Pioneers, aren't they headed down the magnetotail?
Yeah. And
Yeah.
so they'll eventually get out there. It just takes a while.
It just takes a while. You know, and in the meantime, they are performing a lovely service, which is there is absolutely a non-natural source out there in the sky. And if you want to test a piece of software that says, I want to detect non-natural sources of signal, like for alien intelligence or something like that, you run your sky survey, and if you don't find, Voyager, if you don't find the Pioneers, that kind of stuff, then you're not as successful as you think
You have failed.
you might want to be. Well, I wasn't going to say you failed. You've learned something very important.
True.
But
Learned something very
a good way to
So
think
they can-
about it is like those spacecraft are like bottles in the cosmic ocean. And a lot of times you write a message and put it in a bottle that's really saying something about yourself, not necessarily communicating with somebody else, because the chance of finding it is pretty small.
Right.
Exactly.
And that's the
But
way
even-
yeah.
But even the message is interesting. Like creating the message is interesting. I don't know if you guys have seen it, but there's a movie that came out, I want to say just a few years ago, called Farthest.
Yes.
Have you guys seen that?
Yes.
I
actually
had not
have
even heard of that.
I have the DVD of it.
Oh, okay.
Yeah. It was very nicely done. Wouldn't you say, Wayne?
Yeah, it was beautiful. There's a
Yeah.
couple, I noticed on YouTube, there are some individuals that put together like the air-to-ground communications and do a really nice job. I don't know if you've seen any of this, of the different missions, manned missions like Gemini, Mercury, Apollo, and so on. So you actually can see a lot and hear a lot more about what happened back in the 60s and 70s now than you could, just a few years ago. And one of the things they do is also unmanned missions, including the Voyager missions.
Oh,
So,
really?
Yeah,
Okay.
there's actually a lot out there. Like they do the Viking, they do Pioneer. So there's some pretty sophisticated sort of people out there that are putting that the production value of this stuff. So it's actually out there if you actually look for it, which is kind of cool.
Nice. Yeah,
Yeah.
Voyager absolutely has a special place in my heart. Cassini, I was on Cassini for a long time, but Voyager has a special place in my heart.
Yeah,
Oh,
and I'm old enough to
absolutely.
remember, being in K-12 where I would go through like Time Magazine and Newsweek and even the National Geographic when it finally came out, looking at pictures of Jupiter and Saturn from Voyager 1 and 2, and especially the pizza moon, Io or Io, however you want to pronounce it.
And-
All of these things really capture people's imagination. And the thing I think about is how little was spent on those type of missions compared to human rated missions where you need everything backup upon backup upon backup because you're carrying life forms and you got to preserve that, where you could take that same amount of money and really do a lot in the unmanned robotic type of missions, especially nowadays. I mean, look at the drones we're preparing the Dragonfly to go to Titan, for example.
Right.
Yeah.
If you just took, the whole NASA budget for a few years, let's say 10 years, and this assumes you can get people to agree to this. This is the problem, of course.
Right.
Is take 10 years worth of NASA budget, and what can you do for me in terms of unmanned exploration of the solar system?
Right.
And I think we'd get a lot done.
And you know what I want to do? I want to go send a mission to go scoop up some of those tardigrades that crashed into the
Yeah.
moon and bring them back and
See if they're still alive.
see if they come back to life. Because if they do, panspermia just became a real thing as far as I'm concerned. Because
those little guys
cow.
are pretty hardy.
Yeah.
No, the NASA budget way back in the Apollo days was about 5% of the overall federal budget. Most people don't understand how small the NASA budget is. So back then, when we were going to the moon, it was like 5%, and now it's less than 0.5%. So it's half a penny out of every tax dollar that gets spent. And there was a real push for a long time to say a penny for NASA, a penny out of every tax dollar, just 1%, which would basically double the NASA budget. So not as much as when we were going to the Apollo. But there is no shortage of ideas, of places to go and science to do. That's why getting a mission approved is so very, very competitive. And so there is no doubt that NASA could use the money easily for fantastic stuff, and remember, that money, it's not like you put the money on the rocket and it shoots off into space, right? Like that money, that tax money goes to pay for the engineers and the scientists and the builders and the secretaries and the lawyers and all the people that help make a mission possible, because it takes a village to make a mission. And all that money stays here in our communities and is part of the tax base, and yet there is a benefit to humanity that is just writing the textbooks, and encouraging the next generation, right? NASA is something that is just cool. Look at this Artemis mission lately, right? I don't know about you guys, but it just really captured, sort of the zeitgeist out there, and people were really interested in it. One of the things I was going to say, Wayne, was, I appreciate unmanned, in my heart, I'm with you, right? So much more you could do with unmanned from manned, but I appreciate also how humans on the missions, right? A crewed mission just captures people's attention in a different way.
Well, you can always envision yourself being there, right? Doing the exploration. But the other thing to think about is, what other federal agency, people walk around on the other side of the planet with T-shirts with NASA on it, right? Who walks around with a shirt that says IRS on it or something, It compares. And the other thing is, people argue, and this was especially during the time when they're trying to get money out of Congress to vote on it for the space station, the ISS, that they make the argument that for every dollar spent on NASA, you get at least $7 back return into the economy. So not only are you spending money, and yes, it goes into jobs and it keeps people employed and stuff, but you're actually making money.
Right.
What better investment is that when you think about it?
Yeah, a lot of agencies, well, not a lot, several agencies have that, like the national parks. For every dollar that you put into the national parks, you get X back. I forgot what X is, but it's more than $1,
Yeah.
So, but NASA's a very good return on investment. And yes, just think if we could have copyrighted that somehow and gotten the money for all those T-shirts.
Yeah, the NASA worm logo or something.
Yeah. Oh wait, the NASA worm logo, you say? No,
exactly.
I just happen to have this happens to be my mug today.
I like trying to point people out with this. The conversation turns this direction. NASA cannot advertise for itself.
Yeah.
But guess who can? The three of us.
Yeah.
And
exactly.
everybody else out there.
People. Yeah.
So,
people.
I always think, back in a long time ago when I was young, I remember, that family member of mine had collected like Popular Mechanics, Popular Science magazines, and stacked them up in boxes, never threw them away. And I remember going through them as a young person and looking at, and there was one issue that said, okay, in the 1980s, like by the time we end, like 1989, we're going to do this and we'll do that. And we'll have probes on, exploring the icebergs that are floating around Saturn, the ring and all this stuff. And back then, technology was such, maybe we weren't ready. Even if you gave the money, you'd have to give a lot of money to accomplish these tasks. But just look at just drones today. And think of that use, those kind of miniature robotic type of things. Not only could we plan something if we had the money, because we have the technology, that we could send things to go to different icebergs that make up the Saturnian ring system and explore and land there in situ and get samples and things. Right?
Or I love him to death, Les, and his solar sail mission to Alpha
Yeah.
Centauri. You know, let's do these things. Come on.
Yeah. I mean, do them before I die, right?
Right?
Well, the mission to Alpha Centauri, probably not before you die.
No, but
Well,
I mean,
no,
so
but-
does solar. I mean, go to
Actually,
Valles
speak for yourself.
Marineris, right? You
Right.
know, explore
I think
that.
that isn't the solar cell. It's like a 50 or 100-year mission or something like that. But
Yes.
still, you might as well start it. You might as well do it
Right.
and send it on its way. You know, very small little trickle of funding to make sure you're talking to it all the time and is doing stuff.
Right.
You know, have it send us information about the interstellar medium on the way. You know,
And of course, now
Good science.
they stick in the best AI that we have available to run it
Right.
in case communication gets cut off for a while or something, right?
You
You
can
never
make
know.
self adjustments to I forget what the word is, reacquire signal. You know, it can do it
Yeah.
itself instead
Yeah.
of,
Well, think
you
of
know,
Voyager,
over the
as
weekend.
you
I mean,
know.
by the
like-
way, Voyager can do that.
Yeah.
okay, yeah.
It doesn't need an AI. It just needs a piece of programming that where somebody has thought of the fault tree and
Right.
says,
Yeah.
okay, if I'm not getting a signal from the Earth, that could be because my transmitter is bad, or it could be because I'm not pointed at the Earth, or it could be because, you know, Earth has destroyed itself, right? Any number of these things. And they sort of stepped through and they said, okay, first let's reacquire the Earth. Okay, maybe I don't know exactly where the Earth is. Okay, let me find the sun. Let me do a sun search. Let me find the sun, and then let me find the Earth. Okay, now let me switch to the backup receiver. Okay, now let me switch to this. And every one of those, it stays on in that situation for like a day, right? And then slowly but surely, you get to whatever was the actual problem, and you cycle that piece of hardware out of the system. And so, and that's not AI. That's just a very smart, what's called safe. The name of the software is safing.
Okay.
So
But-
and
Yep.
Voyager was one of the first spacecraft to do that. And when they launched, it started. So you know the rocket is tilting over and things like that, and the spacecraft started saying, "Oh my God, it's not. You know, we're getting flipped over. Oh, things are a problem. Oh no!" And it started cycling through stuff. And like people are watching all of these error messages come in, and like the young engineer who was like the real brains behind that safing, he's looking at all this stuff and it's like, no, it's executing the safing procedure. That's what it's doing. And so everybody around him is freaking out. And
Right.
he's sitting there. I wasn't there at the time, but even when I joined the mission 20 years later, they still talked about
Everybody panicking.
Voyager 2 freaking out, right?
Yeah.
And Chris Jones being just like this voice of like, no, it's okay. It's okay.
Working as intended.
Yeah, it's actually one of those documentaries. I don't know if it's the one you mentioned, but other ones. And they said they had barely enough time to make the changes to the limits of the sensitivity of the instrumentation so it wouldn't affect Voyager 1 when it was launched second.
Yeah. No,
So-
they learned.
Yeah.
Because Voyager 2 launched before Voyager 1 because it was on
Right.
a slower trajectory.
Yeah.
So yeah, it was the Voyager 2 launch that caused everybody, swallowing frogs in their throat.
And we have one of our audience members commenting that AI and probes, you want V'ger coming back here? Because that's how you get V'ger.
Yeah, that's how I was thinking about that. But
Yep.
that would show that there's other things out there besides us,
Right.
though, right?
Yeah, that would be definitive proof of other life. Yeah. Our Doctor Who happening, the episode, where it comes back.
And the other thing too, when you think about it, so 89 is when we fly by Neptune, and then Uranus was like, well, everyone remembers that because all the press was over at the JPL when the Challenger blew up in January of '86, and so that's quite a while now. So it would have been nice to have an orbiter, around both Uranus and Neptune before now. And I know NASA keeps looking at it, and planetary scientists want to do that. But just so much was focused on Mars, and because, of course, the support for human missions ultimately, that might have taken away some of the resources available to have, an orbiter around the outer planets by now.
Yeah, that's making me think of. I mean, the reason New Horizons was a flyby on Pluto is because to get out to the outer planets, you have to reach such high velocities, such high
Mhm.
speeds. Do we have the ability to drop something into orbit as we're zipping by, or to pull it into orbit?
Well, if you have enough money.
Well, okay, yeah, yeah. I mean, you
Yeah,
put
no,
Well,
enough
I think
fuel
we
on
have
it.
yeah, we would
yeah.
have the capability of doing that. Yeah.
Yeah, I know Alan Stern. I read a book on the Pluto mission, but I think it was David Brown wrote that book.
Okay.
And
Mhm.
maybe you can attest to some of this stuff because you had mentioned it when we were communicating offline. That as a career scientist, let's say you're ready, or you're done, you got your PhD, you got your first thing you want to work on is to get to some probe that's ultimately, hopefully, will be launched. You could work like 20 years on that project and spend that whole time trying to get all of the necessary funding done, all of the hurdles that you have to jump over to finally get the thing launched. And of course, in 20 years, it may not look like what you had proposed in the beginning because of all the trade offs that you have to do to get it finally approved. So, do you want to say something about that?
Yeah, so it doesn't quite okay, you've got the right sense of it, but you haven't internalized the ages. So for example, if you're going to try to get a mission funded, it's not the young person who's just graduated who has the clout to get a mission funded. It is the older person who has a long history and has worked various missions and has experience and has an idea and has the connections to put together a proposal that's going to be successful. Now, so when you first, so let's just follow a young scientist sort of through their career. A young scientist is in grad school. They are working with a professor who is on a mission, who has data, and therefore there is work to be done. And so the scientific work is done. They learn their modeling, they learn how the instrument, the calibrations. They graduate, right? They get their PhD on data that has already been collected in the past, but they get this experience of working on it. Then when they get hired somewhere, perhaps maybe like JPL or Goddard or APL or a university, right? They're still doing their science with missions that already are in place. And then they become valuable enough. They've got this experience, that's science and operations. They have this valuable enough that then they can be part of a proposal team. Now that and there are a youngster on the proposal team, right? There are people, experts on the proposal team, and there's always one or two scientists, more senior, who bear the brunt of the heavy lift, right? That it becomes kind of like it almost becomes the raison d'etre, right? Like, I am going to get this mission done. This is going to be my thing with the community. So then you're on these proposals, and now you're a full professor. Now you have students of your own, but you're working on that other data. So they're always working on multiple instruments, multiple spacecraft, multiple things with science, doing things in the lab. They've got a lot of irons in the fire all the time. And then they put all this effort into a proposal, and then they nurse it along through the proposal cycle, and then they get it approved. Then by this time, they're looking sometimes at the twilight of their career, as they've gotten it approved, and they're like, okay, well, I'm going to stay on the mission until it gets to its target and it starts doing science, and then I'm going to train the younger generation up behind me so that they could take over. And then you could see how that's the youngsters coming in at the existing missions, but and then in the sort of this middle career / late career, really strong idea, just fantastic scientists. That's who gets the next mission proposed. It's never these youngsters who get the mission proposed. So you had the right idea, just the wrong
Yeah.
age range of things.
Yeah, I guess what I was going to stress is the fact that it takes a lot of time
Yes.
to go through all these hoops. In fact, you may spend a lot of number of years working on it, whether you're a junior
Years.
scientist or you're a senior scientist, and then in the end, it doesn't get funded.
Yeah. No, it's heartbreaking. Yeah, no, and when good missions don't get funded, it is heartbreaking.
It seems like there's a better use of experts' time. Is kind of what I'm getting at. It's not
Well,
optimized.
so I'll give you one of the pros and cons of it. Even though I agree with you. It's gone too far, that we spend too much time and effort. But the pro of it is, it is vetted. It is well analyzed, and nobody, all a ton of experts have looked at your idea and have given feedback that says this is a good use of the taxpayer dollars, and you've thought about it, you've got a good plan. So it's a well vetted. It's a process that creates projects that are well vetted. But I personally would be a little bit more interested in saying I would like NASA to be doing things that are absolutely cutting edge, hardest things you can do. Companies aren't going to do that because there's no profit in it. NASA should be doing the hardest stuff. They should be doing the cutting edge stuff, and they should be allowed to fail. Now, that is an interesting way to think of it, because right now NASA is not particularly allowed to fail. If they do fail, they become the butt of late night jokes, right? People think, oh, you've wasted the taxpayer money, when in fact you didn't waste it. Failure is an excellent instructor. It teaches
Yes.
you. It teaches you what you should have done. I almost feel like anytime a NASA mission fails, there should be a clause right in the thing that says, okay, you failed. Here's the money to do it again and not fail. Right?
Not
Like
fail.
if the science was good enough, then somebody somewhere holds that in a some Congress person, or the Congress holds a little budget line item that says, well, okay, if it fails, we're just gonna spend the money to do it again right away with the same team, understanding what you did wrong.
Yeah. So
But it's a real challenge. I would love to see NASA being so aggressive and doing such crazy things and such hard things that they do fail, and yet but they are not vilified for it. They are in fact, all of us, as you said, Robert, who does this? NASA can't do this. We have to do this. The people, right? All of us, the people, say that's okay. We understood we asked you to do things that were really hard and really difficult, and so hard and so difficult that you should be failing every once in a while, and that's okay.
so failure is an option.
Failure should be. an option.
I would like it. I mean, that's what, going back to your comment, Wayne, from before, is with the robotic exploration, you could have a lot more risk than with
Yeah.
the people.
Yeah.
Yeah.
Right. With people, you'd have to take a lot less risk.
That makes me think of a question I have.
Okay.
Would you say you were in favor then of a lot more smaller missions, CubeSat, little tiny probes that go out with one thing that they are doing, are supposed to do?
So the answer, I think that the answer to that, this is my personal opinion, but is quite aligned with sort of the decadal studies of the past 10 and 20 years, is I think you have to have a mixture.
Okay.
Right. It takes 7 years to get out to Saturn. There's no reason to spend 7 years and then have one instrument that's going to last for 30 minutes. That's a waste.
Fair.
So you need a mixture. You need big missions, you need medium missions, and you need small missions. And I like the idea that we kind of had in the last decade, in the decadal. We have never achieved it, but I kind of like the idea of one big mission every decade, 2 medium missions every decade, and about 5 small missions, discovery level missions every decade. I think that is a very sustainable cycle for NASA and for the community, and I would love to see us achieve that. We have never yet achieved it, but it has been recommended in many of the decadal studies.
Yeah.
Or roughly, those are rough numbers.
Yeah.
They
Right.
are little different every time.
Now these big flagship missions, I'd like to see if they could do things on the way, right? I mean, like, why not have a small telescope you can measure parallax, right? Because you're increasing the baseline, for example, from Earth to the spacecraft. Let's measure parallaxes, and you're out in space, so you can work at the diffraction limit of the optics to measure distances, using that tech, like do other things beside the primary purpose, just to utilize the environment that you're in.
Yeah.
Yeah, I mean it's a tricky balance, right? Because what you're trying to do on your 7 year voyage out to Saturn is you're trying to of course you're going to likely, perhaps not, but likely you're going to fly by Jupiter on your way to Saturn. And one of the things that you want to do in that Jupiter flyby is you want to do a full up exercise of all the processes, all the people, and all the equipment to make sure that you're ready for your science target. But in between that, you sort of want the team, you know, not doing. You kind of want them to be efficient with money, right? You want them to be, kind of want them to be lean, very lean. It's sort of a lean, mean operating machine. You don't want to, you don't want to cycle the spacecraft off unless you have to. I mean, sometimes you have to hibernate. But so typically you're not doing things like the parallax, and I'm not sure. I'd have to think about that, Wayne. I mean, what is 5 AU going to get you? I'm not sure it's going to get
right
you that
now
much.
it's 2 AU, right, from either side of Earth's orbit. So
Right. So
yeah, and then of course you
it's
can increase that distance even more if we're on the other side of the sun
yeah.
relative to the planet. But the other
I'm
thing
just
is too,
not sure.
we do a lot of these gravity assist motions, of course, maneuvers.
Mhm.
Is there any way we could, especially now with miniaturized electronics and stuff, why don't we drop a payload that goes into, a semi-orbit around
Yeah.
these kind of things? Take advantage of what we're doing.
Yeah, so I can tell you why it doesn't happen, and then you can decide for yourself if you think it's a good idea or not. Why it doesn't happen is because it increases risk to the primary mission.
Right.
And so everybody, and right, you've spent $1 billion to get a spacecraft out to Saturn, and you're going to add in a risky, drop off something in Mars on your way. Okay, that would there would be a lot of skepticism and pushback from the review boards when you went into your review boards. Not necessarily a bad idea, but there would be, that's something that would be a hard sell, right? You'd have to have a high bar for what you were dropping off, the value of it.
It almost puts in the category of like the European Space Agency's idea of sending up some probes that are just in orbit around the sun, just waiting for an opportunity. For example, we detect a comet or an asteroid that's on a hyperbolic orbit. Well, we already have the spacecrafts out there, and they could be ion engines or whatever. Let's see if we can maneuver to catch up to them, at least close encounter. So it's kind of in that category where you're taking advantage of an opportunity that you don't have any concrete details,
but
so
I
you
could
can't propose that in the very beginning. But if something happens and arises, we're ready to do that.
But I can see what she's saying, because to do that, you just sacrificed your major mission.
Well, just make it so that literally you're just dropping it, you're cutting off something that has no effect on the primary mission. It's just there, it just unhooks and it goes, or it doesn't go and it doesn't affect anything else. We can minimize the risk, right?
Yeah, I hear you. I'm just saying, having sat on these review boards,
Yeah.
that would be, you would get the skank eye about what?
Right. So maybe we need to change the thought process of the review boards a bit.
That's possible. Yeah. Well, that's where
Sorry.
I would like to see it, NASA taking more risks, right? Maybe this is that area. NASA taking more risks and saying, okay, listen, and if it fails, it fails, you know, but let's take the risk.
Well, one of the things I'm thinking there too is like advanced propulsion, right? So how long are we going to test things on the ground before we're actually going to go into space with it? And maybe the risk taking is to put something up there a little quicker than what we normally would, just to see if it works and get very important feedback on what's happening in, the near term space environment. It could be in Earth orbit, for example, right? Rather than sitting on a bench in a vacuum in space or on the ground somewhere. Let's get it in space, see what it does.
Yeah, there are some technology demonstration missions that they're doing something else, but they're adding a technology demonstration that doesn't do anything for their particular mission, but they sort of had kind of the infrastructure and it was okay and it wasn't very risky. And then they were able to show that and then bring up the readiness level, way up the chain.
That's what happened with Perseverance, and I forget what the little copter was named.
Ingenuity, right?
Ingenuity. Yeah. was kind of that mission, you know, hey, do you mind if we tag along to see if this will actually work? And it did admirably.
Yeah,
So-
I mean, so other things too that I'm curious about. So if you, when you're working on a mission like Voyager, let's say, once you're there, let's say you're in the system, right? They know who you are. They have your social security number, right? Is it easy back in those days to get onto another mission, or is it like the competition is so tough that it's really difficult? And if you do get on another mission or select it, that you're like really lucky and you can be really thankful for that? What's that whole process like?
Yeah, no, it's definitely very competitive, and it's definitely when you get on missions, you're very lucky. And if you, especially if you work outer planets, to work on two major missions in your lifetime is good. Three or four is amazing. And some people have had a little bit of a whole bunch of them just because of sort of the role that they had. But if you are sort of a dedicated, you're working, like for example, I was a scientist who on the mission, so I was a full-time employee on the mission, and for me to have been able to work on three missions was incredible. Most people in the outer planets only get two. And again, I was on Cassini for 20 plus years.
Right.
And Clipper, would have been on Clipper if I made it out to Prime Mission. That would have been 15 or 20 years on that as well. So that would have been the whole career, and then Voyager the first 4 or 5 years, kind of a thing. So yeah, it is very lucky. A lot of scientists who are not on, they can be on the mission, but they're not full, none of them are full time. They are fractions of a day that they put into, they are 4 hours a week on a mission, something like that. And they've got to do their science stuff, right? Uh, um, they've got to argue for the shared resources. They have to help configure the instrument to get the science that they need. They have to do the initial assessment to make sure everything's fine, because they might have another observation coming and they need to fix things. Then they need to do their research, publish their papers. They've got a whole set of things that they do. So a scientist can be on many missions, especially if you have a particular expertise, like you're somebody who works with the camera, and you are sort of an expert at analyzing camera images and images of the surface of Mars or the surface of Europa or the surface of Rhea or Dione out at Saturn, right? It's all a similar skill set. And so you can be on, 2, 3, 4, 5 missions a little bit all the time. But then when you become one of those scientists that is running the missions, then you really have to focus your energies. And usually in the outer planets, you're only on a couple of them. But if you're lucky enough to work in the inner solar system, because the opportunity to have more missions, just because of the nature of the beast, it only takes you 9 months to get out to Mars, for example. So you can have more Mars missions in your lifetime. Many of them have worked, 6 or 7 plus missions.
Yeah, so I assume like, most of the scientists are professors at universities.
Many
Right.
are, yes.
So they can apply funding and say, okay, I'm on this mission. I get the data as soon as it gets back here, and I can have my graduate students analyze the data. So you get paid to do that sort of science. And then occasionally, like if you have a close approach, like think of the Voyager mission, then you would work probably nearly full time for at least some period of time, and then back to your home institution again.
Yeah, no, you've got it exactly right, Wayne, right? When there's a big encounter that's only like Voyager Neptune encounter, everybody, it's like all hands on deck, everybody doing everything for the encounter. And then when you're on the other side of it, you're like, oh my gosh, unbelievable. And you go back to your home institution. And the scientists will get paid from the mission. So there's some scientists that are what are called co-investigators. There's principal investigators for instruments, and they're co-investigators, and they get paid by the mission to do science. But then many of them, as you say, are at universities, and the university will pay for a grad student, right? That is part of the deal, is that that the university pays for a grad student. And so they'll like, okay, listen, I'm on these 2 missions. I can support 3 grad students, and the scientists kind of get their funding from all of these sources. Oh, I'm on this mission and I have 10% of my time. I'm on this mission, I have 20% of my time. The university pays me this much to teach. You know, they put together their funding profile.
Yeah.
And that's one nice thing about the big missions. Again, a lot of little missions are good, but the big missions fund 100 to 200 scientists. And when you're in the thick of it, like when you're in touring at Saturn, hopefully, right, that you're trying to fund scientists at 20, 30, 40, 50%, right? Not all of them, not some of them are more involved, some of them are less involved. There's a natural trade there with things, but you're trying to fund them enough to do the work that you need them to do.
Right. So on a personal level, how was it when you're sitting there during the early part of the Cassini mission after it arrived at Saturn to watch the Huygens probe, do the landing on Titan? That must have just been so cool. Just
I remember your talks at DragonCon on that one, so I'll let you
Unbelievable. Go. It was unbelievable, Wayne. It was unbelievable. So Huygens landed in January. And as Rob can tell you, I am a fanatic figure skating fan. Like fanatic. There's a fine line between fan and fanatic, and I'm nowhere near that line. I can't even see it anymore. I go to the U.S. Figure Skating Championships every year, and I've been going for 30 years. I've gone to the Olympics 3 times. I've gone to Worlds 5 times. So fanatic is the word you're looking for. Okay, so Huygens is landing in January during nationals, and I have been assigned to Titan, and I'm like, oh my gosh, I want to go to Germany so badly. But I was not chosen to go to Germany. I was a minion. I was just a low level science. I wasn't so, but I was in Portland, Oregon. So I called the local planetarium and the local university, and I'm like, hey, I'm in town for nationals for the skating, but I am working on Cassini, and I've been associated with the Huygens probe for this whole time. Do you want me to give a talk? And the planetarium director who I was chatting with was like, is this a crank call? Anyway, so it was glorious, Wayne. The answer is it was glorious. And it was such a success, not only for the team, but like you were watching it live. I mean, I was in bed with my computer watching it live as it happened, because it was, of course, early in the morning, West Coast time. And it was fantastic. And then to have the Huygens probe, just be fundamental to our understanding of Titan, and then all the Cassini Titan flybys fundamental to our growing understanding of Titan, and to have all that lead to then the Dragonfly mission has been one of the things that has been it's been a pleasure in terms of having a long career, is to see that evolution, to see how one mission has questions, they answer those questions, and they ask new questions, and the new questions drive the next mission.
Yeah.
So that's been quite lovely.
I mean, just to finish up the discussion on Titan, I mean, that was a major factor in the Voyager program, because of sending Voyager 1 close to Titan ended its hope of ever going on to the other planets, Uranus and Neptune.
Yeah.
So with the discovery that Titan was completely shrouded in clouds, at least at the wavelengths that the cameras can photograph, there was no point of sending Voyager 2 close to it. So it was able to continue on to the outer 2 gas giants of the solar system.
Ice giants.
Gas and ice. But
we're old-fashioned.
Yeah. But the thing is, I mean, people like Titan was such a mystery before Huygens. Raises this ball of mystery. You can put a question mark on it when you see a picture of it. Say, what is on the surface and what is the interior like? And there's been a lot. I mean, we have a person, which I won't mention his name, who's actually working on a human habitat to potentially be on the surface of Titan. And
fantastic.
I'm on his committee, actually, his thesis committee. And the thing is,
by the way, did you know that there's a humans to Titan meeting in like 2 weeks in Boulder, Colorado.
Oh, wow. I didn't know
Oh,
this.
wow.
This person will probably be there.
Yeah.
Yeah.
But there's a lot of factors you have to consider because you have different types like of precipitation of possibly, you know, organic hydrocarbons and
Which means you can't make it out
things
of
that
organic
can
materials.
eat through your habitat and your spacesuits if you're not careful. I mean, it reminds me of the first Alien movie, right?
Right.
When they land on the planet and the hostile, you know, the wind just roaring and it's just desolate, right? And it's like, okay, you know, is this a place that we should be? Or have we considered everything
yes.
here to lead to a successful mission? So
The answer is yes, Rob. You said no.
Okay. You're right. You're right.
but
You know,
it-
I mean, Titan is the next obvious place to go after Mars,
Right.
right?
yeah.
And just think of all the things that are going to be easy, right? Atmospheric pressure, there's no problem, right? Because you can't breathe it, but it's there, and it makes building things easy, all that kind of stuff. Look at all the methane, the free natural gas that you have for powering stuff. You know, just, I mean, there are just any number of reasons why you would say go to Titan next. And, you know, and I've always kidded that Titan has the largest reserves of natural gas outside of the Earth, of course. And so really the people who should be funding our missions are like Chevron. They should fund us. They should fund us to go to Titan.
Right.
But yeah, Wayne, when you were talking about Titan being the largest piece of unexplored territory in the solar system before Cassini got there, exactly, right? Because when Voyager went, it couldn't see down to the surface. So you had to take a spacecraft with exactly the right types of instruments to see down to the surface, both infrared and radar. And I remember as we were coming up on Titan, or when we were coming up on Saturn orbit insertion, and a few observations from telescopes on the Earth started to show sort of these big things at the surface of Titan that were sort of big splotches of dark and light. And I just remember thinking, oh my gosh, like this entire world, we don't know what it looks like at all. And then here comes Cassini, and it's like, you know, the first pictures that it took of Titan in October, right after JOI. JOI happened in around July of 2004, and the first Titan, and we even had a distant Titan flyby on that just the day after, and that was incredible already. Like all those dark and light things that they'd seen on the surface from the telescopes on the Earth, all confirmed. Yep, that's all there. Here's higher resolution. And then we did a flyby in October. Oh, Lord.
Yeah, I think it was the Keck telescope, wasn't it? That took infrared observations of Titan, if I remember
Actually,
right?
there were several telescopes. There was one down in Chile. There was one, I think Keck was one of them. It has to have infrared filters on it. And I think there was one in Europe. Yeah.
Yeah, and the other thing I remember too, I think during the Cassini mission, you'll know this, is you look back and you take an image of Titan, you get to glint off of the lake potentially, right? Of hydrocarbons. Yeah.
That was crazy. So there's an example of a young scientist, right? Saying, hey, by the way, we should try this. And this was late in the mission. It wasn't early in the mission, right? Early in the mission, things had happened fortuitously. And then late in the mission, a couple of scientists were like, well, we should give this a try, right? We should do this. And then they got a glint off the lake that was, you know, they planned it and it was there. And so that was one of the things that happened late in the mission. And another thing that happened late in the mission, I love this story, Wayne. So again, you've got the older, more mature scientists. They're in there. They're firing on all cylinders. And here comes a young scientist on the radar team. And he's like, hey, we could use the radar instrument in a different way. And we could get the depth. We could use it like a bathymeter. We could get the depth of the lakes. And everybody was like, what? And he's like, no, this will work. And he was showing, because it's a SAR, it's not really an ice penetrating radar, but you can use a radar instrument like an ice penetrating radar, like, you know, if you configure it differently. And so he's arguing to give up one of the very last Titan flybys, not do SAR, but instead do bathymetry over the lake. And in fact, it's that lake right there that's on my clock.
Oh, wow.
Right there. That's
yeah.
Yeah, that's Ligeia Mare. and what I loved about that was he was young and he had a good idea, but he had to stand up to a lot of people and a lot of skepticism and a lot of like, and you want us to give up one of our last, but he had a compelling argument. He carried the day. Science, that's what I love about working on a mission, right? Yes, you have arguments. Yes, you have disagreements, but the coin of the realm is science and exploration and the delta. And so sure, another image of Titan was going to be great and nobody would be unhappy with it. But bathymetry on the lakes, if you could pull it off, was going to be amazing.
Mm-hmm.
And then when we did that, and it was one of the last flybys, I think it was T123, if my memory serves correctly. And I'm like, oh my gosh, I love that story. I love that story because it's the human aspect of it,
Yeah, even planning ahead of time. Too bad they couldn't map the whole surface of Titan, or at least a lot of it.
Yeah.
No, you needed to use the Cassini radar as a SAR radar.
Yeah,
You
so
needed
it depends on the orbit.
Right. Well, right. Remember, largest piece of unexplored territory in the solar system, and the only
Yeah.
thing that can see down to the surface is the infrared camera and the radar. Okay, and the infrared. There were two cameras that had good enough infrared quality to see down to the surface.
Yeah.
And so you needed to map the surface of Titan. You needed to use the radar to get the big swaths, and even so, the radar swaths were thin things all over it, right? And I remember hoping we would get to 22% of the surface covered by the end of the prime mission, and we didn't quite make it. But by the end of the extended mission, we got to over 50%, I think, at SAR resolution because they developed a few new techniques, high SAR and stuff like that, and just fantastic.
And can't you use that information then to kind of lead you to this is where we should go with the Dragonfly in terms of sight?
100%.
Yeah.
100%. Yeah. No, they are using the Cassini data, the radar data, and the infrared data to pick where they're going to go on Dragonfly.
Yeah.
Nice.
Very nice.
We have had a question that's been waiting. We're close to the end of the time, so I'm going to ask it. But we were asked, does Trina think we'll actually have moon bases in the near future?
Yes.
There, that was short.
Well, I mean,
right to the point.
Okay, so I guess we should define near term, right? Near term like 2 or 3 years? No. Near term like a decade? So near term like a decade. Yeah, there's no question that the kind of the next thing we need to be doing is in terms of human exploration is people working and living on the moon routinely. And of course, just imagine the telescope that you could have on the moon, right? It would be fantastic.
Yeah.
So
As long as the dust don't get on the collecting surface.
Yeah.
You have to worry about those kind of things, but
A little bit, but but come on, we've got telescopes. We got telescopes in the deserts here, and we don't we don't say, oh, what if there's stuff that gets on? We figure
but
it
we
out.
clean them, so we have to clean them
So
on the moon.
we can clean. Well, that's what I'm saying.
Well, that's why you
If
have a
had
science team
people-
that's up
That's why I
there.
have a base there.
Yeah.
Yes, if you had people, that would be so. Yes, my answer is yes. But near term is probably something like 10 years.
Well, NASA came out with their announcement today about, I don't know if you noticed or seen it on the news.
Haven't seen it today.
Yeah, it was the next couple of years with the unmanned landing on the moon to bring in supplies and equipment to get ready for this, for a base.
Cool. Yeah.
So we're going to, it's just that as a person that's old enough to remember a lot of other times where we talked about this, like George Bush Sr. and so on,
Yeah.
you get so pessimistic and you say, oh yeah, here's another announcement. How many times have we heard that business?
Yeah.
And so it's always, okay, if it starts to happen for real, if we get to the point where it looks like it's going to happen like a base on Antarctica, then let's go for it, right? But until that time, I'm not putting all of my hope
but
on
we've
that.
had James Owens on here, a good friend of mine, and he was working actively on a team that's designing and building the habitats, the moon base habitats. So,
Cool.
it's cool what they're doing. I forget this company he's working at, but with those balloon habitats and how they do all these pressure tests and all these other tests, and then the final test they do is, of course, I'm tall. test it to braking, and they'll blow it up, and you'll hear that explosion for 3 miles and everything, and it's just like, wow.
Well, it's just
By the way, on
disappointing.
Titan, because the atmospheric pressure is about 1.5 times what you're feeling right now,
Yeah.
pressure test is very easy on Titan.
Yeah.
Just FYI.
Absolutely.
It's just disappointing in a sense when you think about the Apollo project that one of the sort of hiccups was the development of the lunar lander. And here we are in the Artemis program, we're running into the same problem.
Yes.
That we don't have a lunar lander for some reason. It wasn't planned or they did whatever. It's just weird. And we got to rely on, of course, which is a good thing, private industry to provide that lander. But that may be delayed, it could be 5 years before we have something that's at a point where someone's going to trust their life to use it.
Yeah.
So,
yeah.
But anyways, we should end here, Robert.
We should end here.
Thank you.
I hate it. I would love to talk to you more, but
well, thank you very much, Trina, for doing all this stuff.
Yes.
Really
Absolutely.
appreciate it. And for those of you who are
100%.
interested in science or higher learning education,
follow
you
that
get
over.
involved in some of these missions that's going to happen in the future, and hopefully lots of them. You can go to higher learning like the University of North Dakota, and we have both classes online and on campus. We have lots of wonderful programs that you can get involved in anywhere in the STEM or STEAM field for that matter. So please come and join us. Now, our next podcast is going to be a few weeks from now because somebody, me, is taking a vacation, will not be here to help Rob. So I don't want to dump everything in Rob's lap, especially when we have technical problems once in a while like today. I'll come back and everything will be destroyed.
Hopefully not, but
in a fit
you
of
never
anger.
know.
So the next podcast will be on Tuesday, June the 23rd, just so you know that. Now, we also end every podcast with a quote. Now, Trina, you'll like this one.
Okay.
The quote's from Edward Stone.
You already got
Who
it.
is a major, if you like, figure, and Trina, you can kind of address this a little bit, who was the top chief, if you like, of the Voyager program for many, many years.
Yeah, he was the project scientist of Voyager. He was the first one. And he was incredible. And he was all the way until he retired many, because he was there during development as well. So the Voyagers have been flying for 48 years, and he was project scientist even before. And he's one of the most incredible scientists I have ever worked with or encountered in my whole life. And truly an asset to the nation, just incredible. And his work on Voyager, he also was the director of the Jet Propulsion Lab for a stint of time in the middle.
Now, it was interesting. I was searching him up a little bit the other day. There was a picture taken from a meeting about ultimately led to the Voyager project back in 1972.
Oh, wow.
And he's there front and center. So,
he was incredible. Learned so much from him on how to get 100 scientists on the same page, which, by the way, is not an easy task. And he had such skill in that because he had to run. I mean, there were hundreds of scientists on the Voyager project, but I mean, everybody felt like they could be heard. Everybody felt like they had a chance to say what they needed to say, that how decisions were made. Everybody understood what was the process for making decisions. And he was an incredible, teacher by example of how to work in teams, which is something that we all need in university or working on NASA spacecraft. Being good in teams is very important. Yeah. And he was an incredible instructor by example in that way.
Right. So here's the quote. When I look back, I realize how little we actually knew about the solar system before Voyager. We discovered things we didn't know were there to be discovered time after time.
Yep. He was Fantastic. Not wrong.
There you go. Thank you for watching. If you like this podcast, don't forget to give us a thumbs up, subscribe if you haven't subscribed, and thank you very much for watching.
Thank you, folks. See you next time.